Can somebody remind me what a derivative is? I forgot. I'm old. I'm an old man.
Slope.
Okay, derivative means slope. What's a longer phrase that means both derivative and slope? Okay, differentiation. That's a longer word. I agree with you. Like a phrase, the average rate of change. Yes. If I have, and very often in the real world, we can either get a function that describes how much stuff there is at a given time. Well, then how can I figure out how quickly that amount's changing? I take its derivative. And to be really honest with you, in the real world, what we normally see is how things are changing over time, and then we could do what's called the antiderivative to figure out how much stuff is there at a given time. Are you guys at all with me? If you're going into any sciences, and if you're in this class, you must be. Because math is a science too, and if you're a math major, math is the most fundamental science. And philosophy, holy shit, just math, you know, that's amazing. No, gosh. You have to know that's the basic thing we do with science, make observations. The observations we make are limited. We then have to rely on mathematical processes to help us do more than what we see.
Sorry, I said fill in the blanks. Like,
Fill in the blanks, exactly. Can you get that? I mean, there's a whole thing of mathematics about interpolation, which is literally filling in the blanks. Okay, I'll bring it back down, I'm sorry. I just want to keep reminding you, as we learn more and more ways to take derivatives, to differentiate things, you got to ground yourself in why it's important. Because what function could model a real life process? Any frickin' function, yes? I could wear my little dancing dude shirt. Just said all of these functions could be used to model real life situations. So we got to know how to handle all those different functions. Okay. So just to review a little bit, what's the most basic way I can use to figure out the? And I brought no paper with me. Oh, Jeff, you're a mess. Let me see. Here we go. Oh, I got some. What are you? You're a blank. That's all that matters at the moment. Okay. You're sort of blank. Okay. So what do we know so far? The most basic way. Excuse the little items. The most basic way to find, given any function, the most basic way to find the derivative is everybody's favorite thing in the universe, this here. Now, we've used that one time in a very novel way. We didn't look at a specific function. We looked at a specific algebraic manipulation of two functions. We looked at the product of two things, yes? Are you guys at all with me? So, I think I warned you, I'm not going to test you directly on this except maybe one time on the final. But we are going to use the shit out of this thing as we develop new, quick rules. Okay, so if you really, really dislike this poor little guy, you're not going to have to work with him directly too much for a while. So what did we do last time? We said if I have a function that is actually a product of two functions, how do I take its derivative? Does anyone remember what we got at the end? We did some really weird shit. You guys were here? If you were here, we did something that you're like, I would never have thought to do that. I understand. People that only had that to do came up with it after years of thought. So we're just gonna stand on their shoulders a bit, yes? How do I do that? Does anyone remember the rule?
The derivative of f
Good.
times g
Good.
plus f times the derivative.
Yeah, f prime g plus f g prime. Notice something I'm gonna say over and over. You're gonna get so. Some of you guys are like, I'm there, man. You're gonna get so sick of several things I say because I want them to get embedded in your brain. Every derivative rule we're going to look at has this as a component. Every piece gets its own term. Do you guys agree with me? Did f get its own term to have a derivative? Yeah, and the g get its own term to have a derivative. Yep, and then you just add those two contributions together. Okay. I think of it like, I'm going to use this again. Let me think. No, I'm going to leave that alone. Okay. I'm going to leave that alone. So, let me show you a quick, silly example of if we thought products worked a different way. Okay, here's x squared. What is its derivative? 2x, yes. That's one of the best, the most awesome little rules, yes? That's a rule we know. In fact, what is the rule we just used? If I have x to the n, what's its derivative? Where the n comes down?
X to the n minus
X to the n minus 1. Okay. This isn't, somebody just told us that. We developed that shit. It's a shortcut. We noticed a pattern and we said, oh, it's always going to be this. So then I can build off of that. I don't have to use limit definition anymore for things I can put in this form. Now, do you all agree with me? Well, that's the answer, yes? Bam. But do you all agree with me I could rewrite this like this? Now, why would you? I don't know, but you could. So if I do calculus to this, it better line up with what we just did. If it don't, then that means I've applied something incorrectly. Sort of like grammar that I just did. Okay. So if I thought that to take a derivative, I take the derivative of everything at once, like that, what is the derivative of x? 1. And what's the derivative of x? Is that supposed to be the answer? No. So that is a quick, all I need is one counterexample to show, nope, if you have to do a derivative of a product, you can't do all the derivatives at once. They have to each get their own. Now, if I do it the way we just figured out, and again, I am not saying you should write this like this, but just to verify the validity of our process, what if I used product rule now? Is it a product of two things now? Did it have to be? No, but is it now that I wrote it? Like, hell yeah. So if the rule is true, it better frickin' work. What's the rule say to do? Add what? Be specific. Take the derivative of the first times the second, plus the first times the derivative of the second. What's the derivative of x? 1. What's the derivative of x? 1. What's x plus x? 2 frickin' x. There you go. So one of the first level things I'm going to try to remember to do is every time we learn a new process, I'm going to show you if we had tried to use an old process, it wouldn't have worked. And the new process does. Does everybody understand? Never do that shit with x squared. There's no purpose. This was just testing out the logic. If I did write it like a product, the freaking product rule better work. And it do, thank God. Just to continue my awesome graph. Do you have good paper? Probably not, Jeff. Sorry, I had a big Senate meeting this morning, so I'm a little... Oh, what are you? Are you good? No. I see you. Joanne, are you going to help me out?
Yes.
I'm good. I got some stuff. Thank you. I appreciate it. All right. So just to remind you guys, how would I do this kind of a derivative here? How would I find this guy's derivative?
Change. First you want to rewrite it.
Yes. I have a big rant. You've already heard a little bit of it from me that we should have never come up with root notation. It's one of the dumbest things we ever did. Half people, we did a lot of dumb things. You're all suffering the brunt of it on the other end. But do you see how I didn't put a prime yet? Because I'm not about to take this guy's derivative yet. I'm just going to rewrite him. How do I rewrite him?
X to the 3.
How do you remember it?
This.
Where are roots on plants?
On the bottom.
Most plants, bottom. So you just put the root on the bottom. Yes? You guys with me? And then when you do the derivative, how does it work?
Now you can bring that 3, 5 down to the front, and then subtract 1 from the 3.
Yeah, 3 minus 5 is
2.
negative 2. Okay, I like it. So how do you guys feel about the power rule? I can't remember if I actually explicitly said. So again, math people are really amazing with names. You're like, it's x to a power. What do you call them? Power rule. So x to a power. If I could take a function and put it in that form, I could use that rule. So let me ask you this. What you got, Jeff? I don't know, man. So if I have this, that'll work for now. Can I use the power rule?
I mean, you have to put it in parentheses.
What's the rule? Tell me the general rule. If I'm given what? What's the rule? If I'm given what to the what? X to the n. What's n? What's n?
Variable.
What's n?
A number?
Keep saying x. What is n? A number.
Oh,
And of course, what's x? A number, variable. Yes? So we know what to do if the base is a variable and the power is a number. Are you guys with me? You have got to start to realize there's 2 levels to a lot of what's happening in calculus. How do I apply the rule and when can I use the rule? Yes? So a lot of times students get the how to apply it, but they start using it in the wrong places. Does this have the base as a variable and the power as a number?
No.
So can I use that rule?
No.
No. Are we going to learn this eventually? Yeah, just not yet. So right now, we don't have a freaking clue how to take this guy through. Some of you guys might. Just shut up about it. No spoilers. Right? We'll get there. We'll learn. Right now, I couldn't give this to you. If I did, you can come up and kick me in the shin. I couldn't give this to you in a quiz or a test or something. Okay. Not x to the n. I can not use this rule. Okay. You guys kind of with me? This happens in a lot of higher level mathematics. You start to learn, oh, if it's in this form, you can do this stuff. And then students just start doing that stuff to things. Sometimes it's in the hopes that they'll just randomly get the right thing. They're like, I don't know what to do. Let me just try this. No, if it's, okay, I'll stop. See you guys. So if you're really curious what this is, great, keep coming. We'll learn it eventually. Okay. Okay. So coming back, can you guys take a minute? Oh, let's do this. Can you guys remind me what the derivative of this is? Yeah. Does anyone remember what the derivative of cosine is?
Negative sign.
Good. So one thing we're going to eventually do today is finish out the remaining trig function derivatives. Okay, so those 2 things are known. So, could you guys tell me the derivative of, what do you got, Jeff? That. Take a moment, try to figure that out. See, this is the attendance I thought I'd have last time. Because the test was a little rough. Didn't curve it, but it was a little rough.
Oh, that was
Inner, outer.
It was yesterday.
Huh?
Noah versus Brad name.
I have no idea what you're saying.
Oh, it was a
Sorry.
boxing fight.
Oh, shit.
It was on Saturday.
Was
I-
it yesterday?
No.
Oh, dang. My time loop is high.
Were you imbibing when you were? Time just gone. I don't really watch fights, but I did hear there was a fight happening.
Yeah.
What rule are we going to use for this? What's the primary thing about this function I gave you? What is it fundamental?
There's two.
There's
an
two
inner
functions.
and an outer.
Two functions. Not an inner and outer yet. We haven't talked about that yet.
Okay.
There's nothing inside. In fact, what are the two functions here?
X to the
X
third.
to the third. And what's being cubed? X, right? So there's no function of X inside of a cube. There's no inside function. And what is that being multiplied by?
Cosine.
Cosine. And again, what's inside the cosine? Just X. Things are going to get a little freakier if I shove other stuff into a function. That's going to be later. Okay. So I have to use what rule here?
Product rule.
That's insane. So what I try to get students to do, and I understand, number one, that is a G. It just is, I don't know, it's just touching its own nose, all right? Leave it alone. Number two, don't try to take the derivative at the same time you're doing the rule. You're going to get lost. You're going to put stuff in the wrong place. Be nice to yourself. What's the rule say?
F prime of X.
Take the derivative of the first dude
One function.
times the second plus
The second. Oh, the first.
first dude times
The derivative of the second.
derivative of second. Okay, so that does two things. It reinforces in your head what the rule is, and it makes the problem easier because now you could just focus on x cubed prime, right? Taking the derivative of x cubed, that's easy as shit, yes? And the derivative of cosine, which is just a memorization thing, so as long as you have that memorized, it's easy as shit. What's the derivative of x cubed?
3x squared.
That's insane, but also correct. And what's the derivative of cosine?
X cubed to negative sine x.
Good. Now don't leave it like this. Just kind of clean it up a little bit, yes? It shouldn't be a surprise that a function that is a product of two functions will have a derivative that could be more involved. There's a lot going on. If I change the value of x, that changes the value of x cubed. It also changes the value of cosine. So how quickly is g changing is dependent on how quickly each piece is changing. So it should be understandable it's going to become a little more involved. There's going to be more elements. Are you guys at all with me? I just want to make sure. As a student, you desperately try to tell, does my answer look like it makes sense? You can't always tell. But when you're applying product rule, quotient rule, chain rule, all the stuff we're about to get into, the answer more than likely will be more involved than the original function. Okay. So, product rule, let it be nice. Let the product rule be nice. I think the book, I always forget to check, but let's talk about this function for a minute. This function right here is going to become your favorite function. In fact, let me do it this way. Hold this on the back corner for a second. Let's look at this function more generally. If you've ever seen any calculus, you know what I mean when I say this one will become a fan favorite. This one, it's not that much harder. It isn't. There's just one little thing, and people always forget it. Okay, this is the one I just talked about. Remember the 3 to the x? So I guess I'm going to show you right now how to do it. I temporarily forgot. Do we have an idea how to differentiate that? Do we know? Do we? You do? Okay, I'm sorry. I didn't mean to call anybody out. Somebody's like, oh, I'm sorry, I thought we did. We don't have a freaking clue unless you kind of calculus. So if you've never taken calculus before, you do not have a clue how the hell to do that. Because it's not x to the n. It's effectively the opposite of that in a weird way, right? Okay. This is its own function. Do you guys know what it looks like? If you graph it, just out of curiosity?
Can we?
Huh?
Can we?
What do you mean, can you?
Because A is just going to be any value.
Well, let's say A is greater than 1.
Yes.
Even then, if A is not greater than 1, it still has the same kind of shape. It's just been reflected or something. If A is greater than 1, does anyone know what that looks like? Yeah, there we go. Do it again. All right, so that's part of it. So it looks like, from your perspective, this. Yes? It's got what happening at the x-axis. Anyone know? There's an asymptote. Very quickly. You guys someone with me. Does that sound familiar? A to the x. What is A to the first power? A to the first power. A. We assumed A is positive. You with me? What's A to the 0 power? It was anything to the 0 power, especially if it's not 0. What's anything to the 0 power? 1. Yes. Very quickly, since nobody said anything. You guys are all aware that anything to the 0 power is 1, except 0. 0 to the 0 power is actually an indeterminate form we'll talk about relatively soon. Let me stop. You guys are all aware. How many of you guys are not aware or forgot or would like to see why anything to the 0 power is 1? Would anyone like a refresher? Yes? Okay. So those of you not speaking up, that's your hero for the moment. What's x to the 7th divided by x squared? X to the 5th, right? You all with me? So what's x squared divided? How'd you get 5, by the way? What's the shortcut? 7 minus 2. So if you do that same exact thing, what do you get here? X to the 0. Well, what's something divided by itself? 1. Okay. Another way to see it is, if I have x squared, let's say, x squared. What do I get if I divide it by x? I get x. What if I take the x and divide it by x again? I get x divided by x is 1. And why is that? Because what's known to be right out front? What's known to be here but doesn't show up? A 1. So if I keep taking x's away, when I have no x's, the 1 will still show up. This won't show up. Because why would you show no x's? How do you show no? Right now, write down no x's. You're like, I'm done. It would be blank, right? So x to the 0 must be 1. Yes? One more thing. What's x to the 0 times x to the 8th?
X to the 7.
And what's the only thing you can multiply that by that will always maintain the identity of something? What's the only thing you multiply by that won't change what you multiply by? 1. So x to the 0. What's another way to realize it must be 1? Because if 1 is the only thing you multiply by and maintain that identity, it must be 1. Okay, I'll stop. Coming back. Side. What is a to the negative 1? 1 over a. What's a to the negative billion? My scale is questionable and I don't care. What's a to the negative 1 billion? It's a negative power, so what does it mean? Flip it. Is everybody cool with the fact that a negative power means flip?
Yeah.
So a to the negative 1 billion is 1 over a to the billionth power. Is that a really small number?
Yes.
Yes, because we said a is greater than 1, right? So it's a really small number. Is it 0? Will you ever get to 0 if I make it negative 1 trillion? No, negative 1 googolplex, which is an actual number. It's a 1 followed by 100 zeros, which is where the name of Google comes from. Freaky shit. I don't care how big negative you make that, it's not going to be 0, because what's the top always going to be? 1. A to the negative insane is 1 over a to the insane. There's no way it could be 0, because what's the only way a fraction could be 0 is if the top is
0.
And that's always going to be 1 up there, isn't it? A to the negative shit is 1 over a to the shit. You're always going to have a 1 up top. So what does that translate into? A frickin' asymptote, yes? Yeah. And on this side, a squared, a cubed, that just grows crazy, yes? So that's the shape of a to the x. where a is greater than 1. If a is negative, that thing just flips. Okay. How we doing? All right. The more you know how a function looks, the easier a lot of what you have to do with it becomes. So, okay. Now let me ask you this. What's the slope back here? What's the slope? Like right here, what's the slope almost? It's almost 0, isn't it? What happens to the slope as I move along? It gets bigger, yes? And then it just keeps getting bigger forever. Do you see how if I try to graph the slope of this, it'll basically follow the function itself. Do you guys see it? Or at very least, it'll be very close. I don't know if you guys are really with me. Isn't the derivative almost 0 here? It isn't quite 0. So if I plotted the value of the derivative, it would be basically there. Here, the slope looks to be maybe 1. Here, the slope is bigger. So the slope, it might not perfectly follow it, but it should basically have the exact same shape. Does that, on the surface of it, make some sense? You're all like, I don't know what the hell you're talking about. So again, if I look at just the slopes, the slope here is it's just barely bigger than 0, so I'm going to plot the slope. Here it looks to be roughly 1, so I'm going to plot the slope. So the slope should actually kind of follow the function itself. Maybe it's off by a little bit. We'll see. Now, coming back. Do we know the derivative of this guy? Officially in this class? No, we don't have a clue. How do I investigate it? What's the only method we have?
To use some kind of
ChatGPT. No.
a rule, quotient rule.
No quotient rule. I can't do that. Don't even know it yet. I'm going to use the limit.
Oh yeah.
What's the limit? It'll be this business here, right?
Yeah.
Are you guys
That's
semi with me? Are you guys doing all right?
That's what I meant.
Oh, now stay with me. What did I say? I said you're going to see this shit, didn't I? I said you're not going to have it on the next few tests or quizzes. It might show up on the final. But you're going to see this shit because that's the only tool we have to find the derivative. And that's a function we haven't found anything about yet. Okay. So let's see, what does this look like then officially? It would be a to the x plus h minus a to the x all over h. Now watch this. You ready? When do you add powers? Be very specific. When would I add powers? When I'm multiplying, I heard the word product. When I'm multiplying like bases. Yes? You know, we did it earlier. X squared times, what was it? X to the 0 times x to the 8th. It's right there. 0 plus 8 is 8. Yes. So that means, this is very easy to not notice. But can't I break this shit up then? You add powers when you are multiplying the same bases. So what must this have come from? Had a base of a. One power is x times another base of a, and that power is h. I guess. I think students shut down a little bit because you think this is like a type of problem you're going to have to be able to do. No, we are deriving the formula together. You just have to observe and let me know if something doesn't make sense. Okay. The only way this would show up somewhere is like on the bonus part of a test. Rederive the derivative of a to the x. Okay. Anything I can do on the top there?
Kill the 80 to the x.
Can't do like a natural log out of nowhere.
A to the x
right?
minus a to the x.
Isn't that the same in both terms? So I can take them out. What would be left?
A to the h
Good. Minus. Take it out. What's this divided by itself?
1
1.
divided by h.
And this is so cool, and I hope you guys are like, oh, whatever, man. Your definition of cool needs some tweaking, man. I don't even know if you guys have noticed. What part of that expression that's inside the limit don't give a shit about h? What part of this expression don't give a shit about h? A to the x. So I can take that out. It's like a constant, right? According to the limit. What's the limit care about? H. What does he do as h goes to 0? Does he give a shit? He stays the same. No. I'm not letting x go to 0. I'm letting h go to 0. So does a to the x care? No. I need you to understand what just happened. I didn't need those parentheses, but we'll all be okay. Do you see how the derivative of this is equal to itself times a little bit extra? Yes? Whatever the shit this is. We don't have time for this anyway. If you made a table of values, yes, and you did stuff like you plugged in 0.1, 0.01, 0.00, you guys kind of with me? How do I investigate a limit when I'm not sure what L? I do that. Or if we graph it and we follow it along, what you'll eventually get is that this business is the natural log of A. So what did we say earlier when I looked at the a to the x function? It looked like its slope should be pretty close. And sure enough, the derivative of a to the x is a to the x. It's itself times a little something, a little adjustment, because it's not perfectly its own slope. That's trippy. You agree? It's trippy? I'm not sure if you guys are so, what do we do? Now, real quick, can anyone see a special base that I could replace A with? That would make something simplify. So real quick, just make sure everybody understands what just happened. We started with this, and we got the derivative to be this. So if for example, if I had a function 3 to the x like we did earlier, what's its derivative? You could do it. We know what it is for everything. So what is it for this one thing? 3 to the x times natural log of 3. Yes. If it's 3 to the x, what's a? If it's 3 to the x, what's a? 3, because that's what's there, yes? So this is the rule for anything that looks like that. Yes? So let me make sure you guys understand. If I have this silly thing, remember that guy? What's his derivative?
Into x and minus 1.
You guys with me? So if that was a 7, wouldn't there be a 7 here and a 6 there? Yes? That's how you use the rule. So how do I use this rule? If that's a 3, that's a 3 and that's a 3. If that's a 7, that's a 7, that's a 7. Yes? No? Screw each other. So again, so if I had this, what's this guy's derivative?
11.
Yes, yes. 11
times x
to the x times ln.
Oh, ln 11.
11. So the adjustment we have to make. Do you all agree with me that if I change the base, the graph is going to change a little bit? The bigger the base is, the quicker it goes up, and the steeper it is back here. The quicker it goes up, and the quicker it gets to 0. Doesn't that change the slope of it? Let me say this again. If I change the base, it changes how quickly it goes up. That's slope, isn't it? And it changes how quickly it slopes down to 0. No, it just says how quickly it goes to 0. That's slope, isn't it? So that's why it's its own derivative, except I have to adjust it for the base. The base changed my slope, so it's going to show up in the derivative because the derivative is slope. Maybe. So So on one level, you can just memorize this shit and go, I don't care what you're saying, Jeff. I'm just gonna put shit in there. On another level, if you understand why it makes sense, what I just said, it's easier. It's not even memorization there. It's just, you just do it because it makes sense. What base would be a great base? Reminding you A is greater than 1. What would be a great base? What would be the best base? 1. Reminding you that A is greater than 1. What would be the best base? What base would work best with natural log? E. Because what's the natural log of E? What's the natural log of E? What's the natural log of E? Okay, let's do this. Okay. All right. Refresher. What's log base 7 of 49?
7.
Okay, I'm really happy we're doing this. Do we already have an idea of division? If I meant to divide 49 by 7, how would I write it? 49 over 7, or 49 division symbol 7, yes. Now thankfully, math people are not so frickin' goofy that we would make a function and give it a name of a thing you could find in the forest if we already had division. So this cannot be division. So what is it based on? What are logs based on? Exponents. So what power does 7 need to become 49? 2. So the answer to every log question is the power the base needs to become this. 7 to that equals this. So you can always check the log. Yes? Logs suck because it's frickin' word. Square roots are nice because it's just this weird symbol and I can totally associate it. And it's its own thing. We've memorized what the square root of 16 means. What's the square root of 16 mean? What's it asking you to find? Two numbers that multiply to be 16, yes? Or a number times itself, right? What does it take 2 of them multiply to 16, yes? What is a log asking you? How many of these multiply to be this? That's what it's asking you. That's a completely, I'm sorry?
Oh, sorry, yeah, it's just basically asking the exponent.
Yes.
Like, so you basically it's asking for an exponent.
Yes. What power does this need to become that? That's what it always wants. You guys all with me? Now, natural log is a funky little dude. What's the base on this log? No, what's the base on this log?
Oh, that one.
Sorry. What's the base on this log? Good, understood to be 10. Why do you think we would, I don't know, have a log where we just assume it's base 10? Because that's the log that goes with our number system. Our number system is base 10 because we had 10 fingers. 1, 2, 3, 4. If we had 8 fingers, we would have base 8. Whatever the shit that would mean, I'm not going to suddenly start teaching that. I'm sorry if I brought that up. So if I see log of 1,000, what is that asking me? Don't tell me the answer. Tell me what it's asking me. How many
multiples?
How many 10s do I multiply to get 1,000? How many? 3. 3 10s, because it's 3 zeros. Yes? Okay, so very good. What does this symbol mean? What's the base? No, that's base is 10. What's the base of this guy?
E.
Yeah, the base on this guy is E. This kind of question is silly then. What power does E need to become E to the 7th? All right, let me say that again. What power does E need to become E to the 7th? 7. Why does that make sense? Because what are logs fundamentally? They are inverses of exponentials. So they kill each other. The same way that cube roots and cubes kill each other. Logs and bases to a power kill each other. They're the same base. Okay, I like it. How are we all doing? Some of you guys are good with this shit already. That's fantastic. Just sit there and enjoy. Does it make any more sense than anybody else? Logs to me is like one of the first ideas where the amount of trouble students have with it is the most distinct from how fundamentally difficult it isn't. if you just realize the reason square roots are easy, again, it's not a little word. We've internalized the question. Logs, you didn't internalize the question. You didn't even know there was a question to internalize, maybe. So what's a log ask? What's the power the base needs to come to shit inside? That's all it'll ever ask. Okay.
So what is ln then? Ln is just e?
Yeah, so I'm only going to write this once. This is going to, weirdly enough, this is going to physically hurt me. Okay, that's the only flippin' time you'll ever see the shit from me. We just chose, instead of writing this, we chose to do this. Because E is such a cool little dude, we gave it its own little symbol. Does anyone know what E actually is? It's sort of like pi, it's just different numbers. 2.71828, blah, 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 goes on forever, doesn't repeat. Okay, you get it. Just like pi. Why did we give pi its own symbol? Why?
Because.
Why did we give the number 3.14159?
It's a hassle to type out.
So you,
It's because the hassle to
okay, sure, but it's a hassle to type out 7.183942773944487. Why didn't we give that a symbol?
Because is that a constant?
No, it's just
Exactly. Like you're only going to use
No. Why is it a constant? Why did we give it a symbol? Because it shows up all the time when I'm working with
Trig.
Piece of pie.
circles. Okay, and trig comes from circles. So what about E? Well, if we learn a little bit more, I'll be able to show you where E comes from. The stupidest place E comes from, by the way. The stupidest place E comes from. Actually, it's going to be applicable here, I guess. How do I want to write this? N to the infinity, 1 plus 1 over n to the n. This is actually not stupid, I'm sorry for saying that. It's just in comparison to the other place E comes from, it's kind of boring, but this is related to compound interest. If you let n, now let me see if you guys are with me on this. If you let n go to infinity, what does 1 over n go to?
1 over infinity.
Which goes to 0. 1 divided by big ass thing and small ass thing goes to 0. Does it ever get to 0?
No.
If this did get to 0, what would be inside? 1 plus 0? 1. And what is 1 to any power? 1. Okay, you guys with me? So if you don't think about it too deeply, it looks like that limit should be 1. But remind me, does the inside ever actually get to 1? Why not? Because n never gets to infinity. Of course it doesn't. You can't get to infinity. Are you with me at all? So there's two competing things. The inside's getting really close to 1, so the answer should be kind of 1-ish. But it doesn't get to 1, and the power's going to infinity. So on another level, it feels like it should just go infinite. But the inside gets so close to 1, and the power goes to infinity, the two kind of agree on this weird-ass little number that we gave the symbol E. This comes up all the time in business when you're doing compound interest, population growth of various bacteria and shit, yes? So of course we gave it, we're like, holy shit, that's weird, 2.7128, blah, blah, I think that's what it is. I'm very happy I don't actually know for sure, and I'm okay with it. So we're just gonna call this the number E, just like the number pi. What is it?
2.71828.
I always forget.
28.
I got the first two decimals, I'm fine with it.
28, 18,
You guys with me? Have you worked with E before? A little bit. But you've seen it before I said anything about it, yes? How many of you know where it came from? You did? Okay. All right. Not too many. Okay. Do you guys know where pi came from? Did I show you? No. I'm not going to show you. I'm sorry. I could show you where pi came from and not the other. Be quiet. Did the whipped cream? Okay, what the hell was it? Okay. So when you see this, officially, if I use the full rule, it would be e to the x times ln e. But what is ln e? The base is e. So what do I raise e to get e? What do I raise e to get e? 1. So d to the x times 1. So that is a function that is its own derivative. That kicks ass. So if you're like, if I say take 3 of the x, you should go, oh, I'll make that worth all the points. No, but I'm not going to. Are you guys on board? Even when it's got other shit happening, I have to use more advanced rules, it is still the coolest little dude. It's just gonna be himself somewhere in there. Okay. Maybe, Jeff. Okay. So, now that we have product rule, and if I want to write it really quick, it would be like this. So I don't have to write the of x, right? Fg prime is f prime g plus fg prime. You with me? That's not a great way to write it if you're, trying to explain the full thing, but it's a quick little reference. Let's talk about quotient rule. Write it more explicitly. I have a different way to do quotient rule, but it only works if we already know chain rule, which kind of sucks. I'll be okay. So listen, if you weren't here last time, you should watch the video. Remember last time when we did the product rule, we added and subtracted something? Remember that? You guys remember that? When we did the limit definition of derivative, I added and subtracted the same thing. You guys remember that? And it was weird, it was trippy, because you're like, why would I ever think to do that? And I'm like, exactly right. I could do, should I do it? No, yes, maybe. No. I could do the whole limit definition again, and it would look like this. You guys see how? Plug an x plus h into the thing I'm looking at, plug an x into the thing I'm looking at, take the difference divided by h, yes? Do you guys see how I can get like denominator numbers? Like denominator numbers. Just do it, John. All right. Just do it, John. All right. Okay. So let me put this up here again. How do we get like denominator?
Gotta multiply on the other
Yes.
side.
So f of x plus h times g of x minus f of x times g of x plus h all over g of x times g of x plus h. All right, I still need to put the over h. Yes. So does everybody see what I did? I gave this guy a g of x, and I gave this guy a g of x plus h. And it's also being divided by h. So let me just be smart and just shove that thing right there. So it's being divided by h also. So it's being divided by all three of those things. What does the top look like? Doesn't it look like the product rule, but with a minus sign? Doesn't it look like it wants to be? So see, I could do that same trick. Let me see if I remember. I think last time we got a little lucky. All right. Yeah, I want to do this. Minus f of x, g of x plus h, plus f of x, g of x plus h, minus f of x, g of x. Is that the right way, Jeff? No, I didn't. I don't know. I'll have to think about it. I could add and subtract the same thing up top. I don't want to make us sit here and wait for me to remember which. That wasn't the right thing because it would cancel with that thing. It'll be all right. I could add and subtract the same thing up top.
Plus,
Oh, is that what I need? Yeah. I think so.
minus
Wait.
plus minus.
Just hold on, everybody. I think it's this.
Yeah.
Yes. Don't y'all feel better? All right. Sorry.
Should I?
Oh, I left out my other stuff. G of x plus h. That's down there also, right? Those poor little guys. So all I did was I added and subtracted this. Do you guys see that? That's all I did. Just like we did last time. Do you see how I could take a g of x out? So I could do f of x plus h minus f of x all over h g of x plus h times g of x minus, I'm sorry, over here, yeah, here's what I could do. I don't know if you guys are with me or not.
the f of it.
I'm going to factor out a negative f of x. So that this becomes positive and this becomes negative, because now, if I was smart over here, oh, that's right, I'm remembering that's what I need. All right, this is a little bit trickier. What is this?
Your prime. Your rule for.
What is this? The limit of this. You can do it. Yeah. So what is it?
F prime?
Yes, good. F prime. And if I let h go to 0, the bottom becomes g squared. On the top I got g of x. Okay. You only have to loosely follow this. You're never going to have to do this yourself. What is this?
G of prime.
G prime. So this would be f of x, g prime of x. Also over g squared. If I let h go to 0, wouldn't this be g times g? Okay. All right, let me gather what we've done here. I love you guys. I love how you're frantically copying this down. I appreciate it. You're never going to have to do this yourself. Yes? It's good to have, so you know it comes from somewhere. And I used the exact same kind of trick that we used to get the product rule done. Yes? The specifics of this don't matter that much. What matters is the feel of how this came out. We got f prime to show up. We got g prime to show up. And letting h go to 0, these other parts just kind of like come for the ride. Doesn't the top look like product rule except for one thing? How's the top different?
Subtraction.
Yeah, there's a minus instead of a plus. So it's f prime g minus f g prime all over g squared. So it kind of makes sense. If I start with a freaking quotient, if I have a function divided by another function, I should expect my derivative to be even more complicated.
Is it g squared or is it x squared?
It's g squared.
Okay.
Because I'm squaring the g function. Okay. All right, so let me recapture what I just said in a slightly better way. So if I have f over g, that becomes f prime g minus f g prime over g squared. All that crap I just did boils down to this. Real quick, which function at first could you rewrite with a negative power? And it would make sense still. Which function would be written with a negative power if you like forced it to the other side? G, yes? Isn't this g to the negative 1? You with me? You with me? Isn't g on the bottom? So it's g to the negative 1, that's why it's on the bottom. Okay. How do you take the derivative of x to the negative 1? Hold down. Be negative x to the negative 2, correct? You with me? So where I take the derivative of g, do you see how it's negative? Because the negative 1 would come down making it negative. Do you guys see that? There's a song for this stupid thing. Of course there's a song. Stupid song. I never remembered it because it actually rhymes 2 different ways. So that's stupid. Some of you guys know the high, low, blah, blah, blah. Here's my song. Top first. My song is top first. You take the derivative of the top first. And then everything flows after that. Maybe. So just to really make sure you understand. Does everybody you didn't have to follow every step, but do you understand you could see how this comes from the limit definition of derivative? Where does the limit definition of derivative come from? Slope. Just comes from algebra slope. y2 minus y1 shit, yes? So this came from y2 minus y1 over x2 minus x1. That's where it came from. It's more complicated because there's a lot of shit in the middle and we're dealing with things that aren't straight lines, but that's where it essentially came from. Okay. But now you must find a way to memorize this. So let's try a problem out. What you got, Jeff? I don't know. Ooh, let's do something really neat. What about this? I love you guys. You guys are probably still like, your definition of cool, neat. What dictionary are you using now? Do we know the derivative of tangent? Don't tell me if you already took calculus. I don't care about that. Does anyone who never saw calculus before, you know what the derivative of tangent is? Have we done it yet? Do we know? Do you want to do the limit definition? Tangent of x plus h minus n? I don't want to do that shit. So what's a better way to do it? Do we have a way to rewrite it? So it's in terms of functions we know the derivatives of? Yeah, so tangent is what over what? So it's sine x over cosine x, yes? You guys with me? So if you are about to say that, you would have been perfectly right. Right? You're good. I love it. See? Look at that. All you have to do is speak up. It's not a big deal. Do I yell at people if they get something wrong? Do I? I do? I'm sorry. I don't mean to. Listen, I know this really well because I teach all the time. Right? I teach pre-calculus all the time. How many times have you guys had pre-calculus? Maybe 3 at the most, right? How many times have I taught the damn thing? So when I ask a question and you think you know, just give it to me. It's okay. If you didn't get it quite right, who cares? Unless it's you. Whoops. Okay. So how can I rewrite this sine x over cosine x? So what rule can I use now? What rule can I use now? Quotient rule. Kick ass. So how does that dumb thing work? Let's see. What do I take the derivative of first? Top. So top derivative times the bottom. Minus
top left alone, bottom.
Good, top left alone.
Bottom
Derivative. All over.
The bottom doubled.
Bottom square. Yes, that's quotient rule. So if you've never taken calc before, this is your first time getting a quotient rule, you have got to memorize it. By the way, remind me, how do you do x to the negative 1? Derivative? The negative comes down, and the power becomes what? See, isn't that g squared on the bottom? G to the negative 2, isn't that g to the negative 2 on the bottom? G to the negative 1 should be negative g over g squared. Negative g prime, that's what I should say. Okay. So, what's the derivative of sine? Cosine. That's crazy. So cosine times cosine is? Cosine squared. What's the derivative of cosine?
Sine x cosine.
Do it again?
Negative sine.
Negative sine. What's negative sine times negative sine?
Negative of positive sine squared x.
What's cosine squared plus sine squared? And what's 1 over cosine squared?
Cosine.
What's 1 over cosine? Secant. So, the derivative of tangent is secant squared x. Why? Because it is. And again, just to remind you guys, does anyone remember how to graph tangent? What it looks like? Yeah, and there's really neat walls, right? Where are the walls at? Something about pi. That's a good guess. You're talking about trig.
From 0.
Sorry, jeez. I like that. Pi is in there somewhere. So between negative pi and pi over 2. Why is that true? Because what's on the bottom of tangent? What is on the bottom of tangent? What is on the bottom of tangent? Cosine. When is cosine 0?
That's that pi.
Negative pi over 2. So of course there's a freaking vertical asymptote there because the bottom goes to 0 and the top don't. That's the one with infinity. Some kind of infinity. So it looks like a cubic that got stuck between two walls, basically. So it can't go to infinity as a domain. It does repeat, of course, right? Because it's this crazy ass trig function, so it just repeats forever. You guys remember this? Y'all kind of with me. So, what's the slope here? Really big. No, what's the slope? Not the value of the function, but the slope. It's going up, yes? It's really big positive. Then it goes through, does it ever, so right through here, it doesn't quite get to 0 through here. And then it goes back up to really big positive again, yes? Maybe? So that looks like secant, because I don't know if you guys remember, secant looks like it's on top of cosine like this and on the bottom. So if I square it, wouldn't this stuff come up here? I don't know if you guys are all with me. So basically that just repeats forever because this repeats forever, yes? So that's on the level of what the graph looks like and what the slope is. Tangent x does match with having a slope of secant squared. At least visually it matches roughly. If you have no idea what I just did, it's not the most important thing. You gotta memorize tangent's derivative is secant squared. All right, we might as well finish out the trig functions, and then I think I'll give you a break for a bit. I can go grab some better paper. How's everybody doing? You guys all right? Okay, I'll take that as a sure, Jeff. So let's see, what do we got next? Let's do secant. What do you think I'm gonna do to figure out secant's derivative? What did we just do for tangent? We wrote it in terms of functions we knew. All right, I want you to start to realize, now that we have power rule, product rule, quotient rule, I can start taking new functions, functions we don't know, and if I can rewrite them as some algebra of functions I do know, I can get that derivative. I don't have a freaking clue what secant. I don't want to shove secant in the freaking limit definition. There's secant x plus h minus. Oh, screw that shit. So can I rewrite it in terms of a function I know? What would it be? Yeah, 1 over cosine. And then what can I use? Quotient rule. So how do I use quotient rule? What's the song?
Derivative of the top.
Somebody sings the song to make me so happy. Top first. Okay, so top first times the bottom. Minus top times the derivative of the bottom. All over bottom squared. Yes? Maybe. What's the derivative? Now here's what really trips me out about this. What is the derivative of 1? 0. Somebody, I will always have somebody who does this. How is this still here? That is 0, yes? So this whole thing is 0. Good. So g prime equals -1. What's the derivative of cosine? Negative sine. Is everybody with me? So that's 0. Minus 1 times negative sine over cosine squared. How are y'all doing? You're so excited, I can tell. We love this, Jeff. Not that terrible, right? Negative is, you never believe it, it's positive. So then I can say this is sine x over cosine x times 1 over cosine x. See how I can split the two cosines up? Because then, what's sine over cosine? Tangent. And what's 1 over cosine? Secant. So what did we just discover? Is everybody kind of with me there? 1 over cosine is secant. Sine over cosine is tangent. That's a nice way to rewrite that. I don't want to memorize sine x over cosine squared x. I'd much rather remember the way I actually have it remembered is secant x tangent x. So if I start with secant, the derivative is secant tangent. What would your guess be about cosecant? What's the derivative of sine? Cosine. What's your cosine? Negative sine. What's the derivative of secant? Secant x tangent x. What's your guess as to cosecant?
It'll be -2.
It'll be negative. And I'll bet you it'll have the co-shit instead of the non-co-shit. You see how secant doesn't have a co? Its derivative is positive and no co-shit, yeah? Derivative of cosecant just to cut to the chase. We could do the same shit we just did. Yes? But if I start with cosecant, its derivative is negative cosecant x cotangent x. And again, we could do the entire process. The process isn't that hard, it wasn't that long. Just write it as 1 over sine, right? Do the quotient rule. That's what we would get. So now you start to realize something that you couldn't really make sense of when you first took trig. Why the shit did tangent and cotangent go together, but then sine and cosecant, what the shit is wrong with you math people? Now all the co stuff has negative derivatives. And all the co stuff, except for cosine, cosine's an asshole. All the co stuff has co stuff answers, except for cosine, because cosine's an answer. I don't know if you guys are really open. So here, before we go take a break, what's the only thing we have left? Cotangent. And how do I rewrite cotangent? How do I rewrite cotangent?
1 over.
Sure, 1 over tangent would be even better than that. Cosine over sine, yes, it's 1 over tangent, so it's the reciprocal of tangent. So I'm going to do this a little quickly. Derivative of the top times the bottom minus the top derivative of the bottom all over the bottom squared. Yes, that's just quotient rule. So if I do that for myself, I'm reinforcing the rule in my head, and I'm allowing myself now to just focus on derivatives. That's the only thing I have to worry about now. Derivative of cosine is
Negative sine.
negative sine times sine is negative sine squared. Derivative of sine is
Cosine.
cosine times cosine is cosine squared. What's negative sine squared minus cosine squared? What's sine squared plus cosine squared? What's sine squared plus cosine squared? 1. So it'd be negative 1 over sine squared. And what's 1 over sine? Cosecant. Why does that make sense? So if I start with cotangent, its derivative is negative cosecant squared. If I start with tangent, what's its derivative? We just did it earlier. What's the derivative of tangent? Positive
Positive
secant
squared.
squared. Okay, good. Tangent is positive secant squared. Derivative of cotangent is negative cosecant squared. You only have 3 things to memorize then, because the other shit is just analogous to those 3 things. I don't know if you guys understand. So one of the biggest things in math, of course, is how much you have to memorize and how much you just have to know how to do. Don't memorize everything. If you know tangent x derivative is secant squared, cotangent x derivative is negative cosecant squared. You don't have to memorize that separate. It's just the way the co stuff works. Okay. All right, let's take a break. What do you guys think? Want a break? You don't want a break? You do want a break?
Yeah.
How long? You want 15 minutes? 10 minutes? Huh? Longer break, the longer we'll stay. 10 minutes. Take 15. Come back at 2. That's all right. Okay. Come back at 2 o'clock. All day. Oh, did I start? I think I did. I did. Let me go. Quiz on 3, 1, 3, 2, 3, 3. Yeah, I like this. This is perfect. Next Monday. And then we'll have a quiz on 3, 4, and something and something. We'll talk more about it on Monday
So
next.
I think 3/4 is the chain rule. So.
That is true. Next one. So I'd like to have at least 2 quizzes before the test. And you do also. even if you don't realize it. Okay. So 3-1 was power rule, X to the end. 3-2 was product quotient. 3-3 was trig derivatives. The trig derivatives, yes. All right, so let's get into this next weird thing. So everybody got this? Yes, this is kind of like a little review of everything we just did related to trig. Yes. Okay. Just to point out, it's also on page 194 in the book. Yes. Law.
That's exactly what I was going through my notes trying to find again.
Oh.
Yeah, derivatives. I used to have them saved in my calculator.
Oh. Interesting self-report.
Well, everybody should. They're programmable for a reason. I've got a thing that automatically do the quadratic formula in it as well.
Alright, so make sure to
I'll
make
clean
you
it,
use
don't
one
worry.
of mine.
No, I used to.
Alright, so it's in the book if you want, page 194. So, let me do this. Let's take a look at something in two different ways. Okay, what if I had this kind of thing going on? Do you all agree the way it's written, it's a function inside of another function? Yes? You guys all with me? You could simplify this, yes? In fact, let's do that on the side here. The correct way to do this. Now, obviously, the kind of problems we're going to look at are not going to be simplifiable. This is a problem that has an inside function, and I could very easily simplify it. What do I get if I simplify this? Sure, do the cube. What do you get? Do the cube. Do the cube. What do you get?
5.
Do it. You can do it. What's 3 cubed? 27. What's x squared cubed? 6. Good. You all with me? What's this guy's derivative?
6 times 27.
Yup. What's 6 times 27? 6 times 27. You have calculators, it's fine. 3 times 27 is 81.
162.
Yeah, 162.
My brain
X to the
it's fit.
fifth. Now, whatever
That's
weird
right.
shit I'm gonna do here, just like I did earlier with x squared as x times x, just to show you if we incorrectly apply an earlier rule in the wrong place, or we make assumptions, it doesn't work. So then we have to figure out, okay, what do I need to do? So that was the product rule that we came up with, and x times x, if I use a product rule, it actually works.
That's where I saw the 5 at.
So whatever I do here, the derivative better end up being this, yes? If I say, oh, this is just something cubed, so its derivative is just gonna bring the 3 down, and the power comes 2. Does that jive with this? Well, let's see, what's 3 squared? Is everybody with me? Do you guys see what I did? I said, I know how to do x cubed, and this is just shit cubed. All right, so x cubed is 3 stuff squared, so 3 stuff squared. But does that work? I end up getting 27x to the 4th, yes?
Well, you'd have to break that 3x squared twice.
Now, here's the, okay, does everybody understand what just happened? How do you do the derivative of x cubed? X cubed. 3x squared, yes? So if I say, oh, this is just stuff cubed, I'm going to bring the 3 down and make the power 2. Does that match with what we got here? It would have to, of course, yes? Because that function is that function. They can't have two different derivatives then if it's the same function. You with me? You can't say the function's derivative on Tuesdays is this and on Wednesdays is this. That's a very, very complex. Okay. Considering where this came from, does anyone see exactly what number, what factor am I missing to make this answer the same as this? What am I missing? You could do it. Where did 162 come from? 6 times 27. Okay, so what factor am I missing? A 6, and how many x's?
2.
I'm missing 6x squared, yes? Oh, I'm sorry, 1. I'm just missing 1. Not from this, but from this, yes? All right, let me stop for a minute. Does everybody see what I'm saying here? If I took a derivative as if it's just this part that matters, something cubed, the 3, the 3 comes down, and the power goes down by 1, yes? If I do that, though, I end up with an answer that's wrong. How do I know it's wrong? Because that function is the same as this one, and this one's derivative is that. Do you guys see the point here I'm trying to make? You can't assume that earlier rules keep applying even if basic things change. What's the rule that I applied here? X to the n. What is the basic reason that should not be expected to work perfectly here? That's more than x. Whenever the inside function is more than x, the rule we're about to create comes into play. Does everybody understand where the 6x came from? If you don't, it's okay, just let me know. It's not a big deal. Everybody sees that. I'm missing a 6 to make that match, and I'm missing 1x to make that match. How does 6x relate to what's in here? It's its derivative, yeah. Isn't 6x the derivative of the inside?
Yes.
So if I did many more examples with other things inside, exactly the same thing would be missing. It's always the derivative of the inside. So the real answer should have been, if I do it this way, the 3 comes down, the power goes to 2, and I gotta multiply by the derivative of the inside. If I do that, I get the thing I was missing, and it would come out the same as that. Why does this make sense? Let's say you're on a train. You are on a train. Who's ever been on a train? Anybody? All right. If you've never been on a train, do you know what a train is? Can you envision there's a train. You get on the train, it's not going anywhere. It starts to move. The train is moving. There's a rate of speed, a rate of change of position of the train. You with me? Train. Is everybody with me? I get up and I start to walk. Does somebody standing on the ground, if the train's going that way and I'm walking this way, how fast does it look like I'm walking? It's the train plus me together, yes? We are, now the plus here doesn't matter. I haven't figured out a perfect physical representation of this, but do you agree that me inside the train, my rate of change has to mix with the train's rate of change to give the total rate of change of what it looks like I'm moving? Does that make any sense? Okay. I heard some mumbling. You're just repeating to yourself what I said. Like, what's this guy talking about? I don't know. So, the actual rule. All right. You know I can't help but do this. I'm going to show you the limit definition proof. So the kind of function we're going to look at now is this here. It is a function that has a one function inside of another one. So for example, it could be 2x plus 7 to the 9th power. Do you see that? That's this. It could be the sine of 4x squared minus e to the x. Do you see how that's stuffed into another function? Yes? So whenever there is a function inside of another function that is more than just x, this rule will show up. So, everybody Everybody hold on to your hats. This one's a little quick, but it's also the freakiest one. I'm going to give myself more room, actually. So I'm going to look at the limit definition, and just remind us, I'm working with this function, yes? This is every function that has another function shoved into it. You with me? So it'll be it evaluated at x plus h minus it evaluated at x all over h. That's all the limit definition does. The shit I plug into it can get worse and worse, but all it ever does is that. Now, if you thought the stuff I did before was freaky, we're going to do something similar. What did we do the last two times we proved like product and quotient? We had to add and subtract the same thing, yes? Here I'm going to multiply, divide the same thing. Which, as long as they're not equal to 0, it's always legal, yes? You can multiply and divide the top of any fraction by any damn thing you want to except 0. Yes, that's true. Okay. Love you guys. This gets really weird, and okay, here we go. So I am going to do this because I am strange. I'm going to multiply and divide by g of x plus h minus g of x. You guys see these would cancel back out and it would be the same thing I had before? You guys see that? You guys see that?
Yes.
It's like me saying 2 over 3 is the same thing as 6 over 9. I can multiply top and bottom by 3. What do you do? Does this ever become 0? No, because h never gets to 0, so this is never equal to that. This is never 0, so I'm always able to do this. Let me see if you guys are cool with me not writing too much. I'm going to move this h over here, and immediately should see this as what it is. What is this piece here? All I do is move the h over there, yes? What is this? What's the limit of this business? Yeah, I heard it. G prime. So all I did from the beginning was I multiplied top and bottom by the same thing. I'm completely allowed to do that. I could have done top and bottom multiplied by 11w to the 8th power minus sine of 38 4y. It doesn't matter, but this is the one that's useful. Because now this piece is G prime. This piece is freaky as shit. Let me see if I can make this the least freaky I can. This is what I came up with, because I don't like the way the book does this, and I think I'm going to end up doing it sort of like them. For this piece here, let g of x plus h equal g of x plus, make a letter they aren't freaked out about, Jeff. Give me a letter you like. B, how's B? You like B? Do you all agree with me that as h goes to 0, g of x plus h should be really close to g of x? Does that make sense? If h is going to 0, this is going to this, so when h is not quite 0, they're off by a little bit. Does that make sense? Is that okay? Okay. And the little bit, I'm just going to call it b. What does that do for you, Jeff? I don't know. So now I can rewrite this as the limit h goes to 0. Oh, sorry.
Can you move the page a little bit? We can't see it.
Oh, sorry. Let me not put this here yet. This is going to get a little freaky. The limit, let's see, this will be f of g of x plus b minus f of g. So pretty cool with that. Didn't I say g of x plus h is g of x plus b? All over g of x plus h minus g of x. What's g of x plus h minus g of x? What's g of x plus h minus g of x?
G of x plus b.
Minus G of X.
No. G of x plus h minus g of x is b. Isn't b the little bit that they're off by? Alright, so what's g of x plus h? What did I say g of x plus h is? I said it was g of x plus b, yes? That's g of x plus h. What do the g of x's do?
Cancel.
Cancel, yes. Just the same way that x plus h minus x cancel, that's why the bottom is h. So let me remind you, why was this g prime of x? Because this is x plus h, x over h, yes? So that goes to g prime of x. This, let me write it even better. This is f of g plus b minus f of g over b. Do you see the analogy here? G of something plus something going to 0 minus g of that same first thing divided by the thing going to 0. Same thing down here. So what is this limit? This limit will be f of g. I love you guys. That is not, sorry, I left out the prime. This is the derivative, yes? This is the derivative of f of g. The same way this is the derivative of g of x. F of g, g of x. Do you guys see that? What the ever-loving shit, Jeff? That's what some of you guys are definitely saying to yourselves. Doesn't this say, take the derivative of the outside function, leaving the inside, times the derivative of the inside? Do you all agree that this function has a function on the inside and a function on the outside? And what did I say at the very beginning is going to be true about product, quotient, and chain? Every function that's an element of the thing gets its own term. So the outside function, does it get a term all by itself? Yes, times. And then the inside function gets a term. Now, how does this relate to what we just did? How does this relate to what we just did? Here. The derivative of this was the derivative of the outside function. Shit cubed is 3 times shit squared, yes? Times the derivative of the inside function. That's the chain rule. We call it the chain rule because math people are very simple people. We said, look, we linked it. We linked this with this like a chain. So that's why we call it the chain rule. There's no other reason than that. So chain rule just means if the inside is more than just x, you have to multiply by the derivative of the inside. It gets its own term. So for example, let's try some examples. And I have a handout that kind of, we'll see. Let's do one example together and then I'll give you guys a handout. Yeah, let's use a semi-new, let's do tangent of 4x squared minus 7x cubed. I like it, that's yummy. It's always creepy when I say that, but you know, I said it anyway. Come back. Go away. Come back. Now, okay. What's the outside function? Tangent. What's the inside function?
4x squared minus 7x cubed.
You with me? Inside is more than just x. You go, oh shit. Let me look at it as outside of stuff. How do you take the derivative? And I know this is still relatively new, but how do you take the derivative of tangent of stuff? Secant squared is stuff, yes? So the outside function gets its own term, secant squared of stuff. You see how the inside does not change. Tangent of stuff, what's this derivative? Secant squared of stuff. Linked with, what function hasn't gotten its turn yet?
Inside.
The inside. Derivative of the inside. So secant squared came because there was a tangent. This stuff came because this was more than just x. So what's the derivative of this stuff? This is nice. 8x minus 21 x squared. Yeah. And there's really no, you could bring this out front, but who cares? There's not much to do in terms of simplifying the answer. One thing you have to be really careful about is you can't take this in here, yes?
Because it's inside
Please, dear God, don't. You can't break into a function like that. So it might be better to put it out front like a coefficient. Now these we should definitely expect are going to be freaky. They are functions that have entire other functions shoved up in them. They're like a turducken of math, yes? Anybody get that reference? Turduckens, when you put a chicken inside of a duck inside of a turkey.
It's like Russian nesting dolls.
Yes, Russian nesting dolls would have been an even less gross example, Jeff. Oh well. Yeah, let's do one more together here. So we got that. By the way, I want to point something out. What is the what's the derivative of tangent x? Secant squared x. What's inside of tangent? X. So if I do the chain rule, what's the derivative of x? So I need you to understand. Every derivative we've ever done has used chain rule. We just didn't have to think about it because the derivative of the inside is 1 if it's just x. You guys see that? So technically when you say, when do I use chain rule? The answer is always. When does it actually change the answer if the inside's more than x? If the inside's just x, the derivative of x is 1. It's not going to do anything. So here, let's try this one. E to the sine of x squared minus 3x. Now listen, I've heard teachers tell students that they have to know ahead of time how many chain rules they have to use. Now, let me just point it out to you. Do you see there's multiple functions inside of multiple functions? Do you see, this is where I would say Russian nesting doll, right? Mm-hmm. What is the main outside function?
E.
E. And what's shoved into it? Sine of shit. So you don't have to know ahead of time how many chain rules you're gonna, you don't give a shit about that. That's E to shit. Sorry. I used to say if I offend you, just wait a few minutes, I'll do it again, but if you don't like the word shit, I'm sorry. So h prime of x, what's the derivative of the outside function? How do you do e to stuff?
It's just E.
E to stuff. Times the derivative of what?
X.
Nope.
Oh, sine.
Yes.
Cosine.
You guys with me? Derivative of the outside function is e to stuff is e to stuff times the derivative of the inside. This is a chain rule again. I don't have to know ahead of time. I just do it as I see it. So this just comes for the ride. He's done. He's waiting. What's the derivative? Good Lord, Jeff. Do I need more or less of this?
Oh my god, it used to be T.
What's the derivative? What is the derivative of sine of stuff?
Negative. Stuff.
What's the derivative of sine of stuff?
Sine derivative.
No, derivative of sine is cosine. So the derivative of sine of stuff is cosine stuff. Times derivative of stuff. Sorry, you know what? I pulled you over. Say derivative for me. Come on in. It's not me, officer. It's calculus. All right. So there's one more thing for me to do. Yes? Do you guys see that?
You gotta finish.
No. But when I first look at e to the sine, I need you to understand it doesn't matter all the other crap. You see e to stuff. Okay, e to stuff, its derivative. Times derivative of stuff. That's the first time you have to worry about what the stuff is. Do you guys see what I mean? I see very often students try to have the whole problem in their head. I'm like, holy shit, don't do that. No reason for that. So what's the last, I'm sorry. What's the last piece here? What's this guy's derivative?
2x
Yeah, I'm gonna put him out front.
minus 3.
Is that a complicated function? Is that a complicated function? You wanna graph this by hand? Okay, so is that a complicated function? Yes. Why is it not surprising? It was a frickin' function inside of a function inside of a function. Of course its rate of change is gonna be trippy as shit. As I change x, doesn't this change? If that changes, doesn't it change this? And if that changes, doesn't it change that? Holy shit. I should expect the derivative to be involved. You guys understand? A little bit? Now listen, I dropped a lot on you so far today. Let me give you this handout. This is the kind of stuff you have to marinate in, let it sink in, do some examples. So real quick, up top, I put a collection of what I started doing earlier. I don't need the chain rule to do these derivatives because the inside function in every one of them is just x. These very obviously have a function inside of another function. Now, for example, this one, you could do it without the chain rule if you wrote this 5 times and multiplied it out. Do you want to do that? No. How would it do this with the chain rule? What's the outside function?
5.
Not 5.
No, power
5th power. How do I do something to the 5th power? How do I do the derivative of something to the 5th power? What's the 5 do?
5.
Comes down in front of stuff. Jeff. It's like, why can't I see anything? Oh yeah. In front of stuff to the
Stuff. Oh.
4th power times
The derivative of stuff.
derivative of stuff. What's the derivative of stuff?
3.
3 times 5?
15. X.
Always do simple simplifications. Not only should the 5th power determine how quickly this thing grows, but so should the inside determine how quickly this thing grows. Here's 2 different formulations for the thing. This is more closely to what I did. This is using this kind of notation. Okay. Then I give you 2 examples. What did I just do? I froze. Okay. 2 examples. Blah, 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 blah. So go ahead and try out number 3. Call me over if you need some help.
Where you do like easier examples to each into it?
No.
It's not beneficial.
I could have made the base 4. So is e to a power a difficult derivative? Is 2x squared a difficult derivative? Is sine x a difficult derivative? No. So what gets things started here? What's the main idea here? What's the outside function?
E to the stuff.
E stuff, e to the stuff. You could literally write this as e to the stuff. Or you could write it as e to the whatever is not going to freak you out. E to the u. You could do that. How do I take the derivative of e to the stuff? E to the stuff times
2x squared.
2x squared plus sine x derivative, yes. So derivative of the outside function first, it gets its own term, times the derivative of the inside function, it gets its own term. Thank God the outside function is e, because that part I just have to rewrite. That's why I told you, even if these got weird shit inside, it's the real MVP. It just says, write me again. Okay. What is the derivative of stuff?
4x plus cosine.
Done. Yes? You can distribute, but I don't see why you want to. And what about number 4? How would I have to rewrite that first?
Well, there's not one. Oh, this side's not.
How would I rewrite number 4?
So that's
Part of
it
it.
for number 3.
That's it for number 3, yeah.
Always do 2 minutes.
Yeah, I knew people thought there was going to be more. Did you try to distribute and stuff?
No. I just took
More derivatives?
the 2x squared by itself and the sine
Oh.
by itself.
No. Yeah.
I always
One
want to
big
do.
chunk of stuff.
I always want to do more than I'm supposed to do.
Understood. What do I do in number 4? What's the primary thing I need to do before I take a derivative?
You're gonna have to rewrite it.
Rewrite it.
It's
Yes.
not in. I haven't done it, but.
So it'll be tangent of business
So
to the
1/3. 1/3.
1/3. So that is, what's the outside function there?
The one.
1/3 power. So it's stuff to the 1/3. If you wanted to, you could literally write u to the 1/3. Replace all the stuff with like u. You just have to remember it's chain rule. So let me see. Just to show you what that would look like. If I wrote this as u to the 1/3, what's the derivative of something to the 1/3?
1/3.
1/3 u to the negative 2/3. I just have to remember I've got to multiply by u prime, yes? Derivative of the inside. If you have to do that, that's fine. But let's see. I could just do 1/3 in front of stuff to the negative 2/3 times derivative of stuff. Good Lord. This part's done. This part's done. What's the derivative of tangent? Derivative?
Secant.
Secant squared of stuff times
12x.
yeah, derivative of stuff. Oh my god. So again, so when you get to this point, so you know the 1/3 power is the outside. 1/3 stuff to the negative 2/3. Times derivative of the inside, times derivative of stuff. This is now tangent of stuff. What's the derivative of tangent of stuff? Secant squared of stuff times the derivative of stuff. Do I need any more chain rules now? That was neat. What's that sound? So then I do the derivative of this, I'm done, because the inside function here is just x. So what's, I think you're saying, Joanne, what's the derivative of 4x cubed plus 6?
12x.
12x squared divided by 3 is 4x squared. So just pull out little dudes like this, pull them all the way out to the front so they don't get lost at the end. Now that is an ungodly mess of an answer. But every step, I was doing one derivative at a time. There's no reason I had to know what it was going to look like at the end. There's no reason for me to know how many chain rules I have to do. I just do it as signal. Right, the derivative of 4x cubed plus 6 is 12x squared, yes. Times 1/3 is 4x squared, so I just pulled that out front.
So because that tan is not just a tan x, it's a tan with stuff inside.
Yes, tan with stuff. So tangent stuff is secant squared stuff.
And then you're gonna break
Derivative
down,
of stuff.
and then you break
You
down
have to
stuff.
keep doing that until the inside is just x. Then you don't have to worry about chain rule anymore.
I think that's where I get confused. I always wanna.
I'm just remembering now that past Jeff was really smart and he made this whole side, which was supposed to be a 3-1 through 3-3 review. And I forgot it.
We also have on the bottom of the other.
So you want us to start preemptively, or?
No, I mean, this is just something I was gonna do earlier. Let me see.
On this
Why don't we, let's see. Can you identify, can you guys look at all the problems? So this is on the other side of this chain rule sheet, yes? Can you guys identify which problems there have a zero derivative? Have a derivative equal to 0. Look at part F. In part F, what is the variable? B. So B is a variable, therefore that derivative won't be 0. Yes? Don't just look for letters that aren't x. No, that says f of b. It thinks of b as a variable. So you have to do quotient rule there, yes? Potentially. You could factor it potentially. So here's something I tell students all the time. So first off, let's do this. Does anyone see any function there whose derivative would be 0? All right, part B. Why would part B's derivative be 0? It's a constant. Does it change if I change x? It's just always cosine 2, yeah? Yes?
I was just gonna say,
Part D? Yes, look at part D. Does it have any variable dependence? No, so if I change whatever variable, does it give a shit? It is eternally e to the negative 4 plus whatever, it's eternally whatever the hell. But can you understand if a student looks at it and they'll just start to attack it? They'll say e to the negative 4, that's negative 4, e to the negative 5. No, it ain't. It's a constant. All right, now listen. You could choose to look at that like a trick question. No, you have got to know what my constants are, what my variables are. So you know I'm going to give you at least one of those on a quiz or a test. So if I were you, I would just go, okay, before I get into the groove of doing shit, let me just look at this and say, oh, that's a constant, derivative 0, yeah. You guys with it? Everything else is cool. Part E is variables theta, and it has theta in it. What would I have to do in part E? What rule would I have to use? Product rule in part E. Here's something else I always tell students. Look at part F. It looks like you should use quotient rule, yes. But what if you could simplify it? If you could ever simplify a function before you attack it with calculus, dear God, do that shit. Don't you wish that wasn't a quotient? If it wasn't a quotient rule, it's going to quickly. When I was a student, I hated quotient rule. In fact, I have to tell you a secret, I never did quotient rule. what I did was, if I had something that looked like it needed quotient rule, I would just take, for example, this one. I would just take 2x plus 3 to the negative 1, and I would do product rule.
Oh.
Now, that's not very smart, to be honest. And which makes sense, because Jeff was just a student then. He didn't know much. Poor young Jeff. That will work. Do you understand? Because this would be product with a chain. But it's just actually just easier to do quotient rule. I just didn't want to memorize the stupid little thing, because I think my teacher did the song and I hated it. All right, I'm sorry. Real quick. What is the only way this could possibly reduce? What has to be true for this to reduce? You could do it. What's the only way this could reduce?
There has to be a factor.
Yes, b plus 1 has to be a factor. So assume it is. So what would this have to be?
3b.
3b. And what would this have to be?
-1.
Do I get the right middle term? 3b minus b. Ah. Now, if I didn't get the right middle term, I would erase this shit and just do quotient rule. Are you guys at all with me? Dear God, if I give you a problem and there's a chance it will reduce, it will simplify, do that. Because then it got less shit. In this case, look, that is f of b. Yes? That is f of b. What's its derivative?
3.
Frickin' 3. Would you get that same answer if you did quotient rule? Hell yeah. It would take you forever. Not forever. It would take you a lot longer. Yes?
F prime times G minus F G prime.
Prime. I'm not saying there's something wrong with quotient rule. I'm saying there's something wrong with using it when you don't have to. So before you do calculus to a function I give you, take a second and say, can I simplify anything? Is it possible for this to reduce, to combine terms, to something? Yes?
But that'll come with time, right?
Huh?
That'll, like, that understanding will come with time.
Well, you can force it right now. You can force it to become a step. Before I do derivative, let me look at it. Okay, nothing happened. Like this guy, can't do shit. I can see very quickly, can't do shit. So then I started attacking it with product rule, like you guys said. Yes? Maybe. Look at part I. Does anyone have any suggestion on part I? There's a way to make part I look better.
Sine, cos.
Because right now the way it's written, I have to do product rule, right? Which is not terrible. But does anyone know what 2 sine x cosine x is? Anybody?
1.
Anybody? No. Good try. What's sine of? Go ahead. Do it again.
And the sign.
Yes. I think what? Okay. Double angle. Yes. Sine 2x is 2 sine x cosine x. What's cosine 2x? Does anyone remember?
So it's the same thing?
Yep, they're the same damn thing. So if you took trig, they should have shown you that. Real quick.
It's an identity,
Some other trig stuff you should know. What's sine of a plus b?
We just went over that.
I did, we did.
Sine A, cosine
Sine A,
B,
cosine b,
plus cosine A, sine
plus sine b, cosine a. I just always do it like that. Sine's a nice guy, he takes turns. So what is sine of x plus x? Sine x cosine x plus? Sine x cosine x. What's sine x cosine x plus sine x cosine x?
What?
Huh?
2.
No, stop it. What's sine x cosine x plus another sine x cosine x? 2
Yeah.
sine x cosine x. And now what we just done, beep, beep, beep. What's sine x plus x? Sine 2x. Okay, so sine 2x is equal to 2 sine x cosine x. A consequence of the sine of the sum of two angles. Now I want you to really hear me when I say this, right? I'm gonna put some trig identity shit on every quiz, every test. because checkbox, I'm an asshole, and checkbox 2,
Need to know
if
that.
you're gonna take Calc 2, you're gonna have to know all your trig shit. And I'm not gonna let you run into the brick wall of Calc 2 and because I didn't remind you of trig stuff. Now, if you don't have to take Calc 2, you still gotta serve my class, so you better review your trig identities. How do you do that? Did I put something up in Canvas? That's all the expectations of everything?
You can go to the sizzle and
Sorry,
get it printed.
you went through a roller coaster of things. You're like, no, you didn't. Oh, maybe.
Maybe it is.
It's up. It is. If you can't find it, just come see me. You guys gotta look me. I'm not. No, listen. You guys understand. You have to know this shit. This is why you learned it. And if you never took trig, holy shit. Talk to me. We should have never let you in 180 if you never took trig. Now, to be really honest, you guys know the state is trying to get rid of pre-calculus?
Yes.
Yeah, the state, do you guys know we used to teach intermediate algebra, math 110? And the state said, stop it. And we said, why? And then our students suffered after that. And I saw them suffer, and I cried with them, because they knew they needed help with their basic algebra. Now they're trying to do the same thing with pre-calculus.
Well, that's just pathetic. That's a terrible idea. I mean, I can kind of understand with intermediate algebra because they teach it in high school, but they don't teach pre-calc in high school normally.
But we're evil. Math teachers keep people from getting their degrees, so we're evil. So this is what they're doing. They're just taking, saying you can't teach this course anymore. Anyway, sorry. All that's on the side.
Since they took it away, they should let us take it off of our transcripts.
So anyway, you guys have to know trig. If you did somehow get in here without taking trig, just come see me. We can focus on just the bare knuckle stuff that you need for this class. Yes.
That could free me
If you
up.
did take trig and you just forgot all of it, redo it. Okay. I think that's enough for today. It's plenty. Yes. Do what?
I need to stop by